The James Webb Space Telescope, JWST, is acknowledged as the global leader. The observatory is the primary focus of space science. Its mission, to investigate the mysteries surrounding both our own solar system and far-off exoplanets orbiting distant stars, in addition to examining the intricate structures that make up our universe, and where we fit into it. In a groundbreaking initiative, scientists recently pointed the JWST toward a star located 120 light-years away from the Sun. As a result, the powerful telescope has uncovered compelling evidence suggesting the presence of carbon-based molecules in the atmosphere of a possible oceanic world far from Earth, a discovery that has left the astronomical community astounded. But how is this remarkable discovery possible? This revelation offers an intriguing look at a planet that stands in stark contrast to any found within our solar system, while also bringing up provocative questions about the potential for habitable worlds elsewhere in the vastness of space. As we delve deeper into this discovery of an exoplanet and uncover the fascinating details it holds, if you're keen on staying informed about the latest discoveries concerning the universe and beyond, be sure to subscribe to our channel, like the video, share it with others, and activate the notification bell to stay up to date. NASA's James Webb Space Telescope has made a significant discovery regarding the exoplanet K2-18b, a planet 8.6 times more massive than Earth. What makes this image so special? This exciting finding includes the identification of carbon compounds such as methane and carbon dioxide found in its atmosphere. The telescope's detection adds weight to earlier research suggesting that K2-18b may benefit from favorable circumstances for life. It seems to possess a hydrogen-rich atmosphere and a surface covered by oceans. The first analysis of this exoplanet's atmospheric properties, situated within the habitable zone, was conducted using NASA's Hubble Space Telescope, which dramatically enhanced our understanding of the system. It's crucial to note that K2-18b resides 120 light-years from Earth, located within the constellation Leo, and orbits a cool dwarf star known as K2-18. This star lies within the habitable zone of its system. Exoplanets like K2-18b, which fall between the sizes of Earth and Neptune, belong to a very small group in our solar system because there aren't similar planets in our immediate vicinity. The possibility that K2-18b harbors a significant amount of carbon and a hydrogen-dominated atmosphere is intriguing to astronomers. Many experts believe such planets may offer ideal conditions for the search for evidence of existence. The presence of methane and carbon dioxide, along with the absence of ammonia, strengthens the hypothesis that this extrasolar planet contains an ocean beneath the hydrogen-rich atmosphere. Early research has also suggested that dimethyl sulfide, a chemical compound produced by life on Earth, might be detected in K2-18b's atmosphere. Dimethyl sulfide is generated by marine plankton, but the evidence for this compound on K2-18b remains weak and requires additional confirmation. Further observations using the JWST telescope network should help determine if dimethyl sulfide is indeed present in the atmosphere of K2-18b in significant amounts. One astronomer from the University of Cambridge clarified that while K2-18b lies within the habitable zone and contains carbon compounds, it does not automatically imply that life can exist there. The planet's radius, which is 2.6 times that of Earth, suggests that its core might be surrounded by a thick, high-pressure mantle of ice similar to Neptune's. Additionally, it has a thinner surface and an atmosphere rich in hydrogen. Though ocean coverage is anticipated on this exoplanet, there remains the possibility that these oceans may be too rigid or inadequate to support life. However, researchers have succeeded in obtaining the most detailed spectrum of a habitable sub-Neptune planet to date, enabling them to identify the molecules present in its atmosphere. A member of the Cardiff University team explained that this challenge was met by analyzing light from K2-18b's host star as it passed through the planet's atmosphere. Transiting K2-18b is classified as an exoplanet, meaning its brightness diminishes when it crosses in front of its host star. This is how NASA's K2 mission first identified this exoplanet. During these transits, a portion of sunlight passes through the exoplanet's atmosphere before reaching space telescopes like JWST. As sunlight filters through an exoplanet's atmosphere, it leaves behind signals that astronomers can use to identify the gases present. The research team intends to conduct additional studies utilizing JWST's mid-infrared spectrometer to confirm their findings and gather further data on K2-18b's climatic conditions. The team's ultimate goal is to search for signs of life on habitable exoplanets, a breakthrough that could revolutionize our understanding of the universe. Furthermore, the JWST has made other extraordinary discoveries. Astronomers using the telescope have detected complex organic molecules akin to smog or smoke in a faraway galaxy. This is the earliest known detection of these kinds of molecules in the universe. Personally, I find this both illuminating and alarming, as these findings in the farthest reaches of the universe are changing the very foundations of our cosmology. The importance of this discovery lies in the fact that these molecules, referred to as aromatic hydrocarbons, were discovered in a galaxy that formed when the universe was less than 10% of its current age. These carbon-based molecules, which are found in petroleum and coal deposits on Earth as well as in atmospheric pollution like smog, are large and complex, composed of dozens or even hundreds of atoms. What makes this find so remarkable is that such large and complex molecules were formed so quickly after the Big Bang, defying expectations based on our existing cosmological models. To put this in perspective, the light detected from this early galaxy started its journey less than 1.5 billion years after the Big Bang, whereas the universe is about 13.8 billion years old today. This means we are witnessing some of the first steps in the evolution of the universe. What is most impressive is that the detection of these complex organic molecules was made possible by the Webb telescope, which will continue to allow us to make similar observations for nearly a billion more years. If we could observe even further back in time, would we be able to find even more of these molecules, perhaps closer to the Big Bang itself? This raises profound questions about our understanding and the science of cosmology. Until now, previous attempts to detect complex organic molecules in ancient galaxies could only confirm their presence. But with Webb's higher resolution, we can now examine the fine details of where these molecules are located. Additionally, the uneven distribution of these molecules in the earliest galaxy, SP4-1847, remains an unsolved mystery. It is truly remarkable that this galaxy was already as massive as our own, with stars that had generated as much carbon and oxygen as those in the Milky Way, despite being only 1/10 the age of our galaxy. As humanity ventures further into the unknown with this knowledge and insight, we are humbled by the vastness and complexity of the universe. With every scientific breakthrough, the implications of these discoveries are far-reaching. Each molecule detected, each spectral signature observed, contributes another puzzle piece to the story of cosmic evolution. Scientists are now considering not only how these complex organic molecules formed so early in the universe's history but also what mechanisms might have driven their rapid assembly in environments once thought to be chemically simple. One leading theory suggests that the interstellar medium, the matter that exists in the space between stars, may have been far more chemically active than previously assumed. High-energy radiation, intense gravitational fields, and dynamic star-forming regions could have created the conditions necessary to build large molecules long before the first galaxies fully matured. If this is true, it could mean that the basic ingredients for life, carbon-based molecules, were widespread throughout the cosmos from its earliest epochs. In turn, this would radically shift the way we think about the potential for life beyond Earth. Rather than being a rare anomaly, life could be a natural outcome of cosmic chemistry, provided the right environments exist. The JWST's contributions to these theories are invaluable. With its unmatched sensitivity and range across infrared wavelengths, it has the unique ability to peer through cosmic dust and into the heart of ancient galaxies, unveiling molecular compositions with extraordinary precision. Future observations are expected to target more exoplanets within habitable zones, as well as ancient galaxies that may harbor similar molecular patterns. Meanwhile, other instruments aboard the telescope, such as the NIR-SPEC and MIRI spectrometers, continue to gather data on planetary atmospheres, interstellar clouds, and the regions surrounding newly forming stars. These studies are crucial for understanding the life cycles of stars and planets, the chemistry of interstellar space, and the mechanisms that may have contributed to the rise of life in the universe. As we stand at the threshold of a new era in astrophysics, the message is clear: the universe is far more dynamic, complex, and interconnected than we ever imagined. And thanks to the JWST, we now have the tools to explore it in unprecedented detail. Looking ahead, international collaborations are forming to expand the search for biosignatures, specific chemical indicators of life, on distant worlds. Telescopes yet to be launched, like the European Space Agency's Ariel or NASA's upcoming Habitable Worlds Observatory, will work in tandem with JWST to deepen our understanding. But even now, one thing is certain: we are no longer passive observers of the cosmos. We are participants in its unfolding story, witnesses to discoveries that may one day redefine our place in the universe. Reveals more of its secrets, shining ever more brightly. Let us know your thoughts in the comments section. If you enjoyed the video, don't forget to subscribe and turn on the notification bell. As we advance in our understanding of the universe, the James Webb Space Telescope continues to provide us with groundbreaking insights. Its observations are reshaping our perspective on exoplanets and other celestial bodies, pushing the boundaries of what we know about the cosmos. This extraordinary telescope allows us to explore space further than ever before, uncovering mysteries that have long eluded scientists. The discovery of complex organic molecules in distant galaxies is just one example of how JWST is transforming our knowledge of the universe's early stages and its ongoing evolution. One of the most fascinating aspects of these findings is the possibility that life, or at least the building blocks of life, may exist in places we once thought inhospitable. The detection of carbon-based compounds in the atmospheres of exoplanets like K2-18b opens up new avenues for studying potential biosignatures on planets that may resemble Earth in some ways. These substances, such as methane and carbon dioxide, are often associated with biological processes here on Earth. However, their presence in distant worlds does not guarantee that life is present. Instead, it prompts further investigation into the conditions that could support life elsewhere in the universe. The Webb telescope's capacity for analyzing the atmospheres of exoplanets with such precision is a significant leap forward. It allows scientists to detect not just the presence of basic elements but also the complex molecules that might indicate the existence of life. This level of specificity is essential for understanding the potential habitability of distant worlds. As our understanding grows, so too does our ability to detect subtle signs of life, whether they are in the form of atmospheric gases, organic molecules, or other markers that could point to biological activity. In addition to its work on exoplanets, the JWST is supplying useful insights into the formation and evolution of galaxies. By observing distant galaxies, astronomers are able to trace the history of star formation, the distribution of elements, and the processes that drive their growth. These observations of galaxies are crucial for understanding the origins of our own galaxy, the Milky Way, and how it has evolved over time. The discovery of aromatic hydrocarbons in a galaxy that formed only a fraction of the time ago compared to our own is a testament to how much we are learning about the early universe. As we continue to explore the cosmos, with each new discovery, we come closer to answering some of the most profound questions in science. Are we alone in the universe? Under what circumstances can life thrive? How is the universe changing, and what lies ahead in its future? The James Webb Space Telescope is providing the tools necessary to address these questions, offering a window into the farthest reaches of space and time. In the coming years, we can expect even more groundbreaking findings made by the JWST. Its ability to study the early universe, the fundamental processes, and exoplanets that shape the cosmos will undoubtedly lead to new insights that challenge our current understanding. The potential for discovering new planets, studying their atmospheres, and uncovering evidence of life beyond Earth is more promising than ever. With each observation, we are reminded of how much there is still to learn about the universe. The Webb telescope, with its unparalleled capabilities, is leading the way in our quest for knowledge. It is not just an astronomical instrument, but a representation of humanity's curiosity and drive to understand the cosmos. As we look to the future, we can be certain that the discoveries made by the JWST will continue to inspire and transform our understanding of the universe for our benefit, answering inquiries that have intrigued humans for centuries. As the telescope continues to scan the skies, we can only imagine the incredible advancements that remain to come. Whether it's the detection of new exoplanets, the exploration of distant galaxies, or the discovery of life in places we never thought possible, the James Webb Space Telescope is at the forefront of space exploration. Its mission is one of discovery, one that will shape the future of astronomy and our understanding of the universe for generations to come. Each breakthrough made by the James Webb Space Telescope not only expands the boundaries of scientific knowledge but also ignites our collective imagination. It bridges the gap between questions that once belonged solely to philosophers and answers now unfolding through empirical discovery. Future missions will likely be guided by the data JWST continues to collect. Its high-resolution imaging and unparalleled infrared sensitivity enable us to look further back in time than ever before, witnessing the formation of the earliest galaxies, stars, and planetary systems. These glimpses into the primordial universe provide crucial clues about how everything we see today came to be. Moreover, the telescope's collaborative nature, drawing upon the expertise of NASA, ESA, and CSA, demonstrates the power of international cooperation in the pursuit of cosmic understanding. It's a reminder that, despite our differences here on Earth, our curiosity about the universe is universal. As scientists refine their models of planetary formation, stellar evolution, and cosmic inflation, new technologies and methods will arise, many of which will trace their roots back to JWST's pioneering work. Already, researchers are developing more sophisticated algorithms to analyze the deluge of data pouring in, revealing patterns and signals that might otherwise remain hidden. And while the scientific community continues to benefit from the telescope's contributions, its impact goes beyond academia. For educators, storytellers, and dreamers, the images and insights from JWST are profound sources of inspiration, sparking wonder in classrooms and captivating minds across generations. In essence, the James Webb Space Telescope is not just looking outward into the vast expanse of space, it is also turning our gaze inward, prompting us to reflect on our place in the cosmos. With every exoplanet studied, every ancient star discovered, and every light year crossed, we inch closer to understanding not only what lies beyond, but who we are, and how we fit into the grand tapestry of the universe. And so, we look to the stars with renewed hope and boundless curiosity, knowing that the Webb is watching, listening, and revealing, one discovery at a time.